Hi, everyone. My name is Furkan. I work as a software engineer at Autodesk in the Alias team. And Alias is a software for surface modeling tools. It's usually used to design... Oh, sorry, it's not running there. Wow. Now you saw everything. Don't look. I know that. Okay. Alias is a software that's, I think, about 7 or 8 years older than Qt, actually. That's used for surface modeling, usually used in car designs and product designs, industrial designs, yachts and rockets and things like that. And a few years ago, we started a project to replace the GUI toolkit that we were using because it was using a homegrown one called Edwin, which was developed by my manager like 35 years ago. And we only got rid of it about 5 years ago now. And I already had a talk about this 2 years ago. If you're interested, you can check it out. And as part of this, one of our major troubles was making sure that we can take all of this data and then transfer it into this new world that we weren't used to before. And in the past, things were not designed while everything was commingled and everything was happening everywhere all at once. So it was a little bit easier to get things done. But now that we were modernizing the source code, we wanted to make sure that we go with proper separation of concerns, we modularize things, and don't run into the same problem that we ran into of 30 years of kind of hindrance of progress because we weren't able to do much. And the problems we were trying to solve during this project, which eventually took 5 years to finish, was to make sure that we don't create a lot of code bloat in the new part of the code base that we were developing. And we increased developer productivity because that was one of the issues in the past where a designer would come in for a new workflow and it would say, can we do this cool thing? And then we would need to be the curmudgeons and say no every time they ask. So we would need to find workarounds for it, see what we can do. And another thing was dependencies. We had a lot of dependencies between different units, and we wanted to prevent that from happening. And ideally, we wanted to have the GUI side running independently as an empty shell that I think in the embedded world, you do something like this, where we can maybe feed some mock data and then simulate things and see how things work. Whereas in the past, that would not have been possible, but this was one of our goals. And the other one was making sure that the developers are not the bottleneck for designers to do their work, because we have great designers in our team with like tons of experience in the industry as well. And they want to do things to make sure that our users can use Alias properly and fast, because Alias is a career software. Like designers come in, they learn to use Alias, and then for as long as they're employed as a designer, that's what they use, 8 hours a day. Like imagine Vim or your editor for software engineers. And we wanted to make sure that our new system is flexible enough that when a designer comes in, they can tell us, here's what I want to do, and then we can tell them, here's how we can do it, instead of saying no. And the dream for this was to make sure that we have a configurable system that would enable us to have a lot of these different pieces to work together, so that we can have an empty shell maybe designers can use to prototype things on the fly, then they can later on share with the customers, so that we don't need to use like tools like Figma where it's everything mocked, but users can actually use the software itself to test things out on their own. And we wanted to make sure that we remove the developers as the bottleneck for design, because our designers are good. We just need to let them do their job. And our developers want to do their job. They're not that interested in UI design. So we can let everybody excel in their area of excellence. So let's see what this, since now the project is done, I'm not spoiling anything in the presentation from the presentation 2 years ago. I can show you what this looks like. All of this, everything that you see here is, as a spoiler, is driven by that new system that I'm going to talk about soon. And then most of the things that you see here were coded by designers in our team. And the reason that they were able to do that was the new flexibility that we put in place. And in Alias, things can get really complex, as you can see on the other side, on the right side and on the left side, you see the same representation of the different representation of the different representations of the same data. So on the left, you see it as a combo box, but on the right, our designer wanted to have something custom just for this particular purpose. And at the end, we just want to make sure that everybody's happy in the way that they're working. We can provide value for the customers. And ever since we switched to this new system and our new GUI architecture, our productivity skyrocketed. We work much faster. Our customers are happy because we're giving them new tools and workflows that they can work with better. And in order to do that, we needed to loosen up the system, right? Before we had a very rigid system. We need to make sure now we have a loose enough system that can be molded and shaped, but not too loose that we can't even hold it up in peace, right? So we need to strike a good balance there. In order to get to all of that, we first need to understand how we represent data in Alias in the core side. We have this thing, a general purpose data structure called symbol table that has been used for decades. So this is one of those things that we can't really change. And inside of it, we store things called symbols that can represent multiple things. Like it's usually maybe numbers, strings, double, float, an array, whatever that looks like. And then UI, in each tool, we have over 300 tools in Alias, and in each of them, UI is created procedurally like this. Again, this is a legacy that we can't really change because that means another lifetime of working on this otherwise. So we needed to keep this the same. And the challenge is to make sure that, again, all of this can make its way up to the GUI side in an efficient way. The initial attempt was using virtual interfaces. We had a core editor class that was defined in our core unit. It exposed some virtual interfaces to describe what it'll do, if it's open, how it's going to open, what kind of controls that it has inside. And then each of those controls were represented by things we call control base. And each of these were then inherited by different types, like control X, whatever we wanted to represent. They were represented with these two items internally. You can see the interface here. And for the UI side, we obviously couldn't really expose the standard string, for example, and similar things directly to QML side. So on top of the code that we already write in our core side, we needed to also add additional interface to the quick side so that data can make its way up to the QML land. And then each control base like this were needed to be coded individually. What properties are we exposing? We need to set them as Q properties, getters and setters, or I think you could also use member as an alternative, whatever signals that we needed to do, because each of those controls come with various data, and then we need to be informed that data changed somewhere so that we can do something in response to that. And when we were exposing it to QML side, this is obviously a very crude example of it, we would have a repeater in an editor that holds on to a pointer to that editor object that I just showed. And then we would expose a bunch of things from it, because controls would be a list model of controls internally. Then from there, we have a loader that can load different things based on the control base that it's receiving. But we lose a lot of information here because we don't know what kind of information that we're receiving, what kind of type, which individual item we're dealing with. So back then, when we first started, we were really relying heavily on the dynamic aspect of QML. And initially, in order to get things started, this was great because the project started with 2 developers, and then it had to get to a prototype stage where we can see, is this going to succeed or not? For that, it was immensely helpful so that we don't need to be worried about the type system and then just put things together and it'll just work. But later on, as the system gets more complex, this becomes more troublesome. And if we wanted to expose different types other than the standard controls that we had, then we had to use QQML property map to expose additional data. And a drawback for this is we don't know what kind of data we're receiving. We have this dynamic properties, but I need to look into the C++ side and then change it both in the core side and then in the quick side that we're doing so that all of this can be exposed. So in most of these cases, any change that we were doing resulted in 3 different changes in 3 different places and compilations in 2 different units. And if we wanted to call functions, that meant, again, those functions needed to be individually exposed with Q invocables. And if we wanted to add more functions, then you need to add more of them. And then it gets into a mess. Like every time you add something, you have to recompile. And if a requirement changes, you have to add different things. Again, then you have to go into individual cases. And if you don't have the standard controls for it, then you have to find the right place for the custom properties, expose it properly. And like any good developer, we don't do documentation, so people don't know what they're going to do with that information, right? So the cons of this is it's hard to use static types. Each change resulted in multiple builds. And lots of visual interfaces is something that we didn't like because, like I mentioned before, the dream was to remove the dependencies so that we don't rely on any concrete types from the core side. As far as our middle layer is concerned, we're just a bunch of data that just gets sent over. And then this side, this nebulous thing, we don't care what it is. It just does things and we do things in response to that. And as a pro, it was C++. I couldn't think of anything else. So we realized this sucks, both from a developer perspective, a developer productivity perspective, from a rigidity perspective. Really, we're kind of not rigid, but still we are, because we're still adding things to a concrete compilation unit instead of it being something dynamic that any designer can play with, for example, and which was a big selling point for us. We needed to make sure that designers can do their jobs along with us so that we can open up the development process, not just to developers, but to our QA, to our UX engineers. We actually have a designer in the team who writes content, is a UX designer, and she codes. Now she's learning C++. So we are really liberated people in our team. The other realizations were, which also helped us to get to a new solution, were our data, like I showed before, is JSON-like. We have really a structured document that contains a bunch of things. And too much boilerplate code is needed whenever we wanted to expose things. We didn't want that. Virtual interfaces create, again, the dependencies that we don't want. These data types are generics that we can do a lot with because we're not dealing with too many custom things. And we want control over the way that the data flows. Again, going back to the whole being able to run Alias as a shell and then letting everything else happen in the background. So let's revisit. We have a symbol table with a bunch of data inside, which could also, because everything is data in software development, right? We represent everything with data, and then we can represent a menu with another symbol table that can contain other things inside, and we can interpret it in the way that we want. And in the QML side, we have actually a lot of good types that we have an equivalent of that in the C++ side. We have the integer, string, color, point, and we even have the ability to provide custom value types and object types. So this means that we can essentially represent everything that you see up there with QML native features that we have. And even functions can be represented like you see over there. And that the property function doesn't exist yet, but there's a ticket for it to enable it at some point. That's why I put it there. And now what we can do is find a way to get that data somehow and bind it to the data representation that we see down below, and then create a bidirectional connection so that when one changes, the other one can get notified. Okay, just as a refresher, this is one of the many ways that we represent data. We have a bunch of shader balls there, a lot of data on the right side, and the way that these things are represented is decided by designers. We don't tell our code base that, okay, I'm adding this thing now and it's supposed to look like this, right? We just tell them, here's something that needs to represent this data for me, and the user needs to be able to change it, do whatever you like with it. And the way that we represent that, we have a bunch of properties, width and height, and view enabled, a bunch of custom things that we add there to make sure that we can draw things in those shader balls. And we can also add or remove things. Not everything has to be represented in the QML side. And if we wanted to add another title to it later on, a developer maybe added that information, but designer didn't want it. Maybe they want it at a later time. They can just add it themselves without even wanting to talk into a developer. They can just do it themselves, run Alias again, and it'll be there because it doesn't require any compilation. And this system, which I'll get into how it works later, just ties that JSON-like data to the QML side with these properties. And it also, since we're using QML, all the value that we get out of QML, all its features are available to us, right? We can support inheritance so that you can define one base control type that can control the standard things that all controls have, and then inherit from it to add additional things for other controls. We support all the built-in types, and then we can add our own types to it as well. And just for code ergonomics, because sometimes you have, let's say, a menu item. In this case, we have the view. In one table, we have another table that represents a view. And then, since this is JSON-like, we can nest things together in QML side so that it looks more aesthetically pleasing to the eye. And it essentially does the same thing. It taps into that new symbol table model, feeds in the table, and then all of the data inside of it gets populated. And we can also add those control table lists. We use it to hide and show some controls, for example, in our views. And all of this you can call it JSON, a new JSON type or a person type that can have different things. It provides a lot of flexibility for us. The way that it works is similar to how settings work, if you've ever used that type. We have the main symbol table model class, which defines very minimal. I didn't put all of it, but there's not much to it unless just very minimal interface. So that one property, so that we can get a table from whatever else that we need to get that data from, because all of that is set in QML side. And that symbol table proxy type that you see is just a wrapper object, so that whenever we're passing a table, we can put it inside that symbol table proxy as a QObject and then pass it on into QML land so that it can be used properly in other places. And everything else, all the data bindings and notifications and all of that happen once the component is completed. And there's 3 private functions methods that you'll see there. Those are the important ones for the implementation part. Unfortunately, I'm not going to be able to show a lot of the implementation details because it's not public code, but I'll mention it roughly. And even if I showed the code, since it's using our own proprietary data set, it wouldn't really be useful, but you can use it as a starting point as well. And in order to represent the different binding cases, we created these binding symbol property binding classes that deals with different types of binding. Some of them deal with property types, the integer string kind that you saw. Some of them deal with table types, because tables can represent larger data sets. It could be a list of data, or it could be, in the example that we saw before, it could be a person object that has a name and last name and email. And all of that is handled by that type. We have a symbol signal binding type, because when we define a signal in QML side, you can fire that, and the core side can be notified as well. And a special function symbol executor type that we use to execute those function symbols that we pass into the QML side, because once we set those objects, it's set in as a QJS property to calculate things, and then once you call it, that QJS property is executed, is called. Later on, all of that machinery makes its way down to this TUI function symbol that we have internally. In component complete call, we first, we have the table. We need to first listen to this table, see whatever's happening. So we need to connect to all of its properties, symbols to be notified. And then the other one is if we have a valid table, then we initialize it. In initialize section, we have a cache that we go through, because this initialization can happen multiple times for performance reasons. We don't really destroy these things. We cache them whenever something gets added or removed. They just stay there. When we get a new data type, we can just get it from the cache, so that we don't spend all of that time setting up a lot of the machinery. And it goes through all of the methods first to see if there's single signals that were set. And it has a lot of error checking internally to make sure that the data that we're declaring in the QML side matches the data that we're actually requesting from the core side. The properties are handled here, and since we have a table that can contain other tables, we also iterate through all of the tables and do something similar to what you see above, so that all the changes inside of it can also make its way through the QML side. The last step is to make sure that the connections are made, but we have not yet updated the property. The last part is just updates all of the properties in the QML side, and everything else can happen in reaction to that in the QML land. And you'll see here that we'll listen for different things and take different actions based on what happened. If a table is removed, maybe we had a person object, then that person object gets destroyed. But if a table was removed, then we had a list of person objects, then that only one person is removed from that list. There's a few edge cases that we need to take care of here, depending on the type of data that you're representing in the QML side. One extra thing that we need to do for executing functions is a bit of a trickery like this with the QJS engine, because once we pass that information to QML side, the QML side needs to have some sort of QObject to call into, because we're not keeping track of these internally. So that little snippet of code there creates a function object that returns another function object, which binds this property to the argument that's passed to it, so that when somebody calls a function, it'll call this.call, and this object refers to our QML function symbol executor, which contains enough information for it to be able to call that underlying C++ function. And then, since we're calling a JavaScript function, it supports everything a JavaScript function supports, so we can have return types from there as well. And also you can pass as many arguments as you like. That you can see over there in the argument section. There's a for loop that goes through all of it and then passes on to the symbol function that we have, which was an interesting challenge as well, to be able to support this calling convention from C++ side as well. And you can see here, there's a bit of a syntactic sugar that you can use until we get that function property type. I just annotated like so that it's obvious that this is going to be a function at some point. And you can also put arguments names there as well, just for show if you're interested. But once symbol table model runs, it'll actually overwrite all of that. So it really doesn't matter. And we also get our return types. And at a high level, in most of these cases, once a symbol table is passed on to the QML side, on the core side, we call model UI side, and all that side, all the code deals with is just those data objects. We don't care about any of the machinery that's happening in the QML side. So the code has access to a symbol, and it does a bunch of processing based on that, and it says, now an information changed, inform the user. It calls notify on it. When notify is called, the symbol connection that we have in symbol table model listens for it and then determines what to do based on the information that we have about that particular symbol. If you remember back to the symbol table listener that we had, it had to deal with different types, and this has to similarly deal with different types as well, but all of that is kind of abstracted into the symbol binding property that I mentioned before. And then once that does its thing, the QML side gets notified, and then you can do whatever you like in response to that. And then later on, you can change something in the QML side, and it'll make its way back into symbol table model. That'll notify the symbol, and then that symbol will notify whoever user was using it in the model UI side, and things will happen accordingly. And so it's a very reactive system. So if you're not careful with it, you can really mess things up. It'll slow down the system because you're doing a lot of things in response to a bunch of symbols being changed or bindings being evaluated. And sometimes we run into this, but profilers help. And we don't tend to do a lot of heavy processing in bindings in our code base, so it hasn't really been a big problem for us. And as a result, we can, this is on the left, we have the object lister and the information window. All of these can contain millions of objects because it's representing each node in our model with additional information inside. So on the right side, you see a node, but internally it represents a lot of other things. So those things will need to be represented in the user interface as well. The beauty of the system is whenever we add a new node or new objects to this, the related QObject side or the related QML-related machinery don't really need to happen until it needs to be displayed in the view. Until that happens, we just have the table that we created in the core side already. It's already ready-made. And if something needs to happen, it makes its way up to the quick land and it gets into view. The list model, the view says, now I need to show something. This is the item that I'm interested in. Give me the information for it. And then we create the underlying machinery. But since we also have caches, we don't do a lot of, after maybe the first use, you won't be noticing a lot of slowdown. And in our code base, we haven't really run into much of a slowdown related to this. Most of them were about actually some of the ways that we were doing in the core side and then the way that it reflected in the UI. And another performance improvement that we needed to do was related to that QJS engine execution that I was doing, which is naturally slow. And there we had to come up with some optimizations, but overall, the system has not really slowed down. It's pretty snappy as Alias before, and our users are very sensitive to performance problems. We have, for example, a thing called marking menu that once you do a clutch, it'll display a bunch of menus for you that you can use a certain gesture to execute things. And they can sense a millisecond of change in the way that shows up. Like we spend actually, if I say months, it would not be an exaggeration to make sure that that's optimized enough for users to not complain about it. So far, we've been using the system since the initial implementation was in 2021, I believe, and we released 2024. And ever since then, we've been using it. And it's a very integral part of the system because any bug that may show up there, it'll affect everything. Because, like I mentioned before, since we have a single place where all of this data is flowing from, that also means we have a single point of failure. If something goes wrong there, everything will go wrong. So we have a lot of unit tests surrounding it. We also have some performance tests that we do during those unit tests to compare if we're falling far behind of what we're measuring. And next up, we need to look into how QML compiler extension can be used for this. I have not tried it yet, even though it's been out for a while now. And we also need to make introspection and debugging a little bit easier because sometimes it's hard to follow where the table comes from and what's inside the table. So it gets a little bit challenging, but the declaration of these things are usually made in the QML side, but what we call the template side, where developers have more control over it. But our designers know how to look into that so that they can see, even if something is not being used, they can look into the code and see, okay, these are the properties that are exposed. It has not been used for design purposes yet, but maybe this is the thing I can pick up to implement several other UX workflows. That was it, but I can maybe get questions now if there are any, because I was told to do additional bonus content. Before I get to that, I can take answers. Question. I can take answers too.
Yeah. So do we have any questions so far?
Hello. I was curious if you'd consider replacing the QtJS engine with another solution, potentially maybe like a Rust engine or something.
A Rust engine?
That doesn't exist yet, but I'm working on it.
What would be the purpose?
The idea would be there's a lot of overhead in all of the different bindings, and obviously like JS property has that its own overhead built into it. Mm-hmm. If you could get that to be compiled into, say, like a Qt plugin that you could load dynamically, it might be a little faster.
Potentially, I guess. But since we're using QML itself and it's JS heavy, and the evaluation of that doesn't take significant time, and there are some optimizations that you can do with caching and a few other things to improve the performance. That hasn't been a problem. But if a Rust engine exists, I'm sure we could even rewrite it in Rust, I don't know if that's still in fashion, but we didn't. I'm interested in actually figuring out a way to reduce additional QObjects that we need to create. So I'm looking at other solutions. And right now, when the symbol table is loaded, once we hit component completed, we run all of that. But I want to find a way to lazily initiate those so that until a property is being accessed, the underlying machinery doesn't get created, so that at least the initialization of those things can speed up time. But you make a good point about the potential performance effect of the JS engine, which it did show up in the profiler.
And do you have another question? Here we have Dennis first.
So you mentioned performance was not an issue for you, but what about memory? Like in general, was it an issue?
The beauty of Alias is that it's usually run in high-end machines with very powerful GPUs and RAMs. But we did run into a memory issue, interestingly though, not in the way that we were handling this, but in the way that we were creating a lot of symbols in the core side. So the cause of it wasn't actually the implementation for the symbol table model. So we have a solution for the lazy initialization of these properties, and also lazy initialization of tables come into that as well. The beauty of it, again, with the flexibility that we have, what we can do, because we know until an item comes into view, none of the tables, none of the machinery gets initiated, right? Since we know that, we can use that information to say, okay, once this thing is created, I'm going to run a function to tell the underlying machinery to say, hey, now you can create some additional initial symbols for me because I need it. And then when it gets out of view, I know that because, again, view tells me. And then I can tell, okay, I'm done with these. You can get rid of it. And that's how we're going to solve the memory problem. And that did pop up. That's a good point.
Right. Yeah, thanks.
Do we have any other question? Then if not, I guess you can continue with your bonus content.
All right, bonus content. This was one of the most fun and also hard to work with parts of the project, the docking implementation. Initially, I'll let this running as I didn't put a lot of slides for this one. Initially, we had some window management implementation in Alias Classic, which we had magnet windows. They would be stuck together. The users would move it around. We had a very primitive implementation of docking where windows would go into the main window, but would stay as an external window, and the main window would just draw with some offset to make sure that it's here. And then if you move the main window around, you could see all the docked windows lagging behind. It would like just come slowly behind it. And since this project was to make sure that we provide better workflows for the users, the UX was very interested in coming up with a proper docking and window management system. We looked around for a bit, and this was, I want to say 2020, 2021 maybe. There weren't a lot of viable options back then. KDAP dock widgets, I think, that was there. And at the time, I remember trying it, but the widget side looked good. The quick side didn't look that well. So we had to come up with our own implementation. I'll let this run again. Initially, we tried a pure QML implementation, which was very foolish. It was a good exercise in frustrations with QML for maybe a month. And then we quickly realized, nope, that's not the way to go, because our windows, we have, at a time, a user can have maybe 3 dozens of windows open if they really want to. And in order to manage all of that properly, we really needed some low-level interaction, because the user also needs to drag things around, resize it, and we need to have control over how the windows inside of it will be resized. In one of the screens, you'll see that if it gets resized, all of them get proportional resized and a few other things. So later on, we switched to a C++ implementation from the quick side. And that gave us a lot of benefits. And one of the things, again, that we kept in mind when we were implementing that was high levels of customizability, because we're already giving designers a way to customize and do their own work. In a lot of cases, we can't create a system that's not flexible enough for them to flex their design muscles, right? A lot of the bells and whistles that you'll see there with all those highlights, and you'll see these arrows here. Where's the mouse? Oh, okay. So these arrows that you see here, the way that they collapse, you'll see it in a bit, the way that they change their transparency. Most of these things. Oh, and then there's another feature where if this window gets small enough, it'll go from being a tab to a tiny sort of slider-looking thing, so that user can get more space out of the windows. A lot of those were actually implemented by designers. Maybe at times they had a need for a certain feature that didn't exist, and we would come in as developers to give them some tools. But outside of it, most of these ideas were designed by them, implemented by them, which probably is part of the reason why the project took 5 years, because it's a gigantic. Alias is 38 years old almost. Lots of things that we needed to change, and we could use all the help we could get. And designers really came in handy in that way. The high-level features of the docking for us is fully customizable. Like I mentioned, everything that you see them as tabs, for example, when we dock them together, but it doesn't have to be a tab. You could show it as a circular image if you wanted to. You have all the freedom around how you want to display information, because even our designers actually got used to thinking in terms of data. When we're designing these things, they first think, what data do I need? And then think of representation of it, which helps a lot in giving them enough creativity and probably letting off a lot of responsibility from the developers. It's completely data-driven. We do use the symbol table models that I mentioned for this one. and it's very easy to serialize it and then load it back. We have a feature, I'll show it in here again. We have a feature called workspaces. Oh, you can't see it, but okay. So underneath the tabs that you see with default, subdivision, visualize, those are different workspaces that users can switch between, and each workspace can have a different window configuration, a different docking configuration. And switching between those need to be very fast as well. And this is where we can run some of the performance bottlenecks, because when users trying to switch from one to the other, if anybody uses Blender has something similar, and switching between them is pretty fast. And we needed something that's pretty fast as well. And the symbol table, everything that you see there is, for example, represented using symbol tables, but we didn't really run into any issues regarding that. If anything, maybe sometimes creating windows were a bit of a problem, but we could get over those problems sometimes easily, sometimes very hard. The last part is very flexible. In fact, in the beginning, it was so flexible that we needed to make it less flexible. It was causing problems for us, because you could go like vertical docks, turn it into a horizontal dock, and then put another vertical dock and another horizontal dock. It really go when all the turtles all the way down, sort of thing. And then eventually we ended up stripping a lot of its features, which felt really nice. After doing all that work, you had to take a lot of features down, and at least UX was enjoying the process. Some of the main components of this is, we have, one of the things I actually like about this implementation is we don't rely on a specific window class. You can bring any type of window that you want and attach. We have an attach type called docking attach type, and that is the one that's responsible for instrumenting some of these machinery underneath to let it communicate with the underlying main dock controller structure. So if you have your own my company window.qml file, it can still work. You just need to attach a docking property, and it'll do its job underlying. So we don't have a special implementation of a window that you have to inherit from and all of that, which I really like. And the base type for it is main dock controller that has a layout that it needs to have so that it can lay things out properly. And that layout can also be configured so that in here, let's see if, okay, we have the windows in that way when docked on the left side, but maybe you want it represented in some other way. Like you have, I can't think of what representation you could have there, but you have the freedom to change a lot of things there. You could put input a new positioner there. You could just put them, I don't know, in a circular shape if you wanted to. Main dock controller is the one that really controls everything else. So we have the dock controller that you'll see, the big ones here. Let's see if this will, oh, it didn't work. Let's see if this flips. Okay, the dock controllers on the left side, you'll see that contain the multiple windows. And individually, once you dock them, where you see the tabs, those are called docking groups, that they can contain multiple other windows internally. And again, you can customize how those docking groups are displayed or how the dock controllers are displayed. We have the docking data model, docking group model, docking controller model that is self-explanatory. We just put in some information there. And the hotspot that you see on the far right side is the highlights that you see whenever a window is being dragged around. We also have declarative support, so you don't have to use a model to show your things. You can nest a bunch of controllers and groups together to initialize docking. And a lot of customization points, we make sure that we're not relying on many custom implementation of items. There's only a few cases where we needed to do that because we needed some additional controls over the way that the events were being redirected. But otherwise, everything else, you just plug it in and it'll work. In this case, you'll see the content item for the docking layout, and it could be a split view, it could be a column, whichever that you prefer there. The docking group can have its own tab bar and stack view. But if you don't want the tab bar, again, you don't need to put it. You can just put a stacked view or display them in a different way. I don't think it's demoed here, but we have a feature where if you right-click over the tabs here when they're grouped together, it'll show a preview of the window popped out so that without switching to the tab, you can interact with the window, click out, and it'll go back into its place. The customization, dock controller. All right. And this is the window that we use, that window implementation existed before we started docking, and we didn't change anything about it for it to start using docking. You do get some information about it when things happen, when things get detached or undocked, they're being dragged around. And if you want to change the title based on whatever you're displaying, you can do those as well. The pain points for this were many because of the event redirection that we needed to do. The event handling happens a little bit differently in the Qt Quick Clan, and we had to find ways around it, even for our menu items, for example. And this is among those pain points. We need to, once you grab a window from the main dock controller, that once you undock it, that event needs to persist, but also needs to be now redirected to a new external window. And that was a little bit trickery. We also have developers working on macOS, so we had to come up with different ways for macOS and Windows. It was a bit troublesome. The item size management is a little bit difficult because things happen out of order sometimes, and you expect them to be in a certain size or have their layout happen, but it doesn't happen. So unfortunately, in that code, I don't like it, but we had to use a lot of deferred calculations, do some call later calls there to get over those problems. But overall, it was really a success story for us. The implementation is very much liked by our customers. And if anybody has any interest in this docking implementation, please let me know, because I could try to get my managers to maybe approve an open sourcing of this project and all that if I get a sense of the interest from the community. And that's all.